So can you hear me, students? Can you hear me?
Yes, sir.
Thank you. So in the last class, we started the Smith chart, correct? And we have seen particularly the R circles, and we derived as well from the voltage reflection coefficient formula these things. So just quickly revise all those things, and then we'll jump over the X circle. Fine. So this was the thing, if you remember. So I'm just writing the summary quickly so we can recall all those things. So what we have seen actually in the last class, that that this equation we try to manage right on this was the circle of the equation, and based on these things, the first thing was that the center of all or R circle lie on the gamma R axis, correct? So center of all R circle lie on the gamma R axis. This was the first thing. Second thing was the R is equal 0 circle means unity radius and center at origin. Fine. And third point was the R circle become progressively small as R increases from 0 to infinity. Fine, because the radius was 1 upon 1 plus R, correct? So if you are moving from 0 to infinity, correct? So R circle become progressively smaller. Fine. The last point was all R circles passes through at gamma R is equal 1 and gamma I is equal 0. So all the circles like this point, correct? I'm just mentioning over this figure. So this was the thing, this was the R circle. These are the R circles, and this is the axis we just talked about. And this is the point, correct? And this point is 1 comma 0 point where all circles are passing actually. And this is also we are calling as an open circuit. Remember, this is also calling as open circuit. Fine. So like this is a center actually. So we can make an axis here like this. This is gamma I, and this axis is what? Gamma R. Fine. And these are the different resistance circle is at different values. Correct. So the outer one is R is equal 0. Correct. And gradually the things are going down. Fine. Okay. So these are all the R circles. Now the second equation. Now the second equation, what we have seen, we can also do some rearrangement and we can write down in the circle format, correct? So that will provide us the X circle, reactant circle. Okay, so let us talk about the reactant circle. So like from the last equation, I'm recalling that x was 2 gamma I divided by 1 minus gamma r to the whole square plus gamma I square. Correct? Now, if we can do little bit rearrangement, like gamma r minus 1 to the whole square, we can write gamma I, this things, square is equal to gamma I divided by x. Fine. Now, if you open it, these things, you have to make the perfect square actually, what we did in the last class, correct? So what you need to do actually, you need to add and subtract. What you need to add and subtract? 1 by x to the whole square, correct? 1 by x to the whole square. So I can write these things, gamma r minus 1 to the whole square plus gamma I whole square minus 2 gamma I over x plus 1 by x to the whole square minus 1 by x to the whole square, for making actually the circle equation or perfect square actually. So the thing is, if you try to club these things, so a very nice equation we can get is like that, gamma r minus 1 to the whole square plus gamma I minus 1 by x to the whole square is equal to 1 by x square. Can we manage? Yes. This is the same term we written here. This term, and this term, correct? Sorry, this term, correct? We clubbed here and we written a perfect square, and this we kept in a right hand side. So now we have this equation, and this equation could be compared with the equation of the circle. Now from this equation we can write the circle center point and the radius. So the center will be 1 comma 1 by x, fine, and radius will be 1 upon mod of x. Fine. So now the life is easy now, correct? And we can plot it on the reflection plane. Fine. We can plot it on reflection plane. So it means what actually, we can conclude some of the facts here, that the center of all x-axis lie over gamma r is equal 1 line, correct? And for inductive reactance, it lies above gamma r axis, and for capacitive reactance, it is below gamma r axis, correct? I'm writing all those things. So it's important point, please note it down. The center of all x-axis, x circle, sorry, lies on gamma is equal r line. Another point is for inductive, because this is a reactive circles, so it is going to represent the capacitive nature as well as the inductive nature. So both the things we need to see. That is why here you will see these things. So for inductive reactance, it lies above gamma r axis, and for capacitive, it is below gamma r axis. It is a really very important point. Okay, and finally we are going to conclude all those things, and it will be arrived for a particular applications, correct? Now the thing is, as I told you, that all reactive circle pass through the point, this sense gamma is equal gamma r is equal to 1 and gamma I is equal 0. This is one thing, correct? So this could be verified as well, correct? From the circle equation, if you put all those things, so you will find that let's say if I'm recalling that equation, gamma r square plus gamma I minus 1 by x is equal 1 by x to the whole square. Now, if you satisfy these things, okay, you are putting 1 here, 0 here, so you can see that both the sides will be equal. So LHS will be RHS. Fine. So these things we can prove these things. Now, let's say at x is equal 1, okay, from x is equal to 1. So can we modify this equation? Yes, of course. So for these things, we can rewrite gamma r minus 1 to the whole square plus gamma r minus 1 to the whole square and 1 whole square. Okay. This will represent actually what? The inductive circles. This will represent inductive circle. Whereas at x is equal minus 1, okay, x is equal minus 1, the equation becomes gamma r minus 1 to the whole square plus gamma I, sorry, this is gamma I plus 1 to the whole square is equal 1 whole square. So this is for capacitive circle. Fine. So, like, if I draw these things, just a minute. So if I draw these things, so it will be like this. We can mark x's first. Fine. And this point is 1. This is minus 1. This is plus 1 again, and this is minus 1. So we can expect a square actually, these things. So for x, when if let's say x is equal to infinity, correct? If x is infinity, what is the radius? These things. If x is infinity, what is the radius? Radius will be 0, correct? So this point, correct? So gradually, these things, when you are decreasing the x value, so the value of these things radius will be increasing, correct? So how we can write actually? So let us make one square actually first. Okay, because the circle is going outside from this 1 by 1 square. This is a normalized value, correct? So let's say if you're trying to draw for x is equal to 1, correct? So what is the radius? The radius will be 1. Fine. It means that this would be the center, and from this point you will making a circle like this, correct? This is the center and this is the value of 1. And because we are interested in this region, okay, minus 1 to plus 1, so we'll be taking only this much, correct? I'll show you the things. And so it means that this is x is equal 1. Now if you are taking x is equal to 0.5, let's say, okay, so what is the radius? The radius will be double, correct? And the circle will be like this, okay, like this. Fine. And if x is equal to 0, so you can expect a infinity radius. So this will be like this. It will follow a flat, just things like that. So this is for x is equal 0. This is x is equal 0.5, like that. In a similar way, you can take minus 1, minus 0.5, correct? Like that. Fine. So in this way, we are drawing the circle, but the thing is, the region of interest is this box. This is square actually, minus 1 to plus 1. So whatever the things are coming, we will be drawing with a continuous line. But this center, if you follow and taking the radius, it will be a circle. It's going out from this thing. So I'll show you in a picture, then these things will be clear to you. Just a minute. Okay, so these things, correct. So here what you can see actually, so these are the circles actually. We are taking this thing some point, and we are actually making a circle, correct, like that. So whatever the part actually falling, this things -1 to 1 and -1 to +1, correct. So we are taking, so here these lines actually, these lines particularly is the x circles, correct. These lines are the x circle. So now we can compare actually these things, like for x is equal to infinity, this is the point, okay, and the radius will be 0. So that is why this is the point. When you are taking, let's say x is equal to 2 or x is equal to 1, let's say x is equal to 1, correct. So what will happen, that the radius will be 1, okay, the radius will be 1. What will be the center point? The center point will be what? 1 comma 1 by x. It means 1 comma 1, okay. So center must be somewhere here, correct. Center somewhere here. What you need to do, you need to take the radius 1 and you will draw a circle, okay. So I'm taking this much part from this point actually, from this part. So these things, similarly, let's say if x is equal to 2, correct. So the center will be 1 comma 0.5, right. So somewhat here actually, these things, this point, and you are making a circle of radius, these things, which is 1 by mod of 2, 0.5, correct. So this will be the circle. So we'll be taking only this part, because this is the, this thing is falling between -1 to plus, like that. So in this way we can make the infinity number of circles, correct. We can make the infinity number of circles, okay. Just a minute. Fine. So simply what I can say, like if you are trying to draw actually circles, fine, it will look like this. These all are reactant circles, correct, and of the different values, like 5.0, 2.0, 1, 0.5, 0.2, like that. And similarly the downside, -5, -2, -1, -0.5, like that. Fine. So the thing is, these all are called as a X circle or reactive circle. Now there's a one thing you need to keeping in mind, that the upper half, correct, the circle, upper half of the circle will represent the inductive reactance component, whereas the lower side will provide you the capacitive reactance component. Fine, because these are the negative values. You can see these are the positive, j omega l, and remember the j omega l, this is the positive, and minus j 1 upon omega c, okay, is a negative. So this will be, negative side will be offering you the capacitance phenomena, correct. So finally, now we have the X circle, we have the R circle. Now what we need to do, we need to merge these two, because these things will be happening at the same time, correct. We are not going to analyze the X circle alone or the R circle alone, correct. So just quickly make a summary here of the Smith chart. So I'm writing some of the points. It's very useful. So the first is that the gamma is actually here is under root gamma r square plus gamma I square. Fine. And the plane actually, what is the reason of interest? What I talked actually, this is mod of gamma less than and equal 1, means gamma plane. Fine. And over that we have seen the R circle and X circle. Fine. Point number 2, these R circle and X circles are orthogonal to each other. at every point. Fine. Now the third point will be the intersection of R and X circle. Fine. The intersection of R and X circle will provide you a point which is actually what? Normalized load impedance or normalized impedance. So getting the real impedance, you are supposed to multiply with the Z0 or characteristic impedance of the system, correct? So the actual impedance you can calculate, like let's say if you are calculating the ZL, so ZL will be Z0 or R0 into R plus JX. Remember we normalize with respect to R0. Huh? So for lossless system we have taken, that is why we have taken the R0. Fine. Other important points are that gamma R is equal -1 and gamma I is equal 0 is corresponds to the short circuit. Whereas gamma R is equal 1, gamma I is equal 0 is corresponds to the open circuit. So these are the some of the points you need to remember, correct? Okay, so I hope this picture is clear to you now. Fine, that the construction of the Smith chart. So here now you can easily visualize all those things, that these lines actually, if I make a trace over here, let me choose a different color. So let's say yellow color, correct? So please check the trace. So these circles are the R circle. Oh sorry, X circle, correct? And finally, when you merge this one, which is a R circle, and the X circle, so you have a bit different picture. Fine. So this is actually the Smith chart. So this picture actually you can see. So we have both the circles, correct? So this is what? This is the R circle and this is the X circle. Fine. I hope this thing is clear. So this is actually what? The construction of the Smith chart. Now the Smith chart actually it's really very useful to get the idea about the unknowns for different RF applications. Like let's say if you are matching issues, correct, this could be solved here, because easily you can find it out the nature of the system, whether it is capacitive or inductive, correct? So you can easily find it out the things that what is actually happening, visualize, you can properly visualize, correct? So other important point is that like VSWR, okay, voltage standing wave ratio. If you remember, so the formula was the starting this. So VSWR, if you remember, it was 1 plus mod of gamma divided by 1 minus mod of gamma. Or we can also write it this things mod of gamma in terms of VSWR. Let's say defining VSWR with S. So this will be S minus 1, S plus 1. So for S is equal to, let's say 2, this is one of the very critical value, correct? Because at this value that we are expecting that almost 90% power going into the device, because showing that the reflections are in an engineering tolerance, correct? So this is a very critical engineering limit actually. Now with respect to this, the gamma mod of gamma will be 1 by 3. Fine. Okay, so the thing is you can plot it over here and you can find, I'll tell you the different scales over the Smith chart, correct? Now let us see a very important thing, that is Smith chart in terms of the polar coordinates. Right? So what is that? Just give me a second. So I'm copying this once again. What I'm going to do, that Smith chart in terms of polar coordinate. Fine. How we will do this thing? So let us define some of the point over here. So this point, what is the point? This is actually the open circuit. So this is gamma OC is equal to 1. Fine. And this point is gamma SC is equal minus 1. Fine. Now let us draw some of the angles over here, correct? Because we are going to deal with the polar coordinates, correct? So let me draw an axis over here. So let's say this is the center. So this vertical one and this horizontal axis. So this is, let's say, gamma I, and this is gamma R. Fine. Can we because the thing is this is a reflection plane. Okay, reflection coefficient we are going to deal here, and reflection coefficient we know that it comes with like that. Fine. So there is a magnitude, yes, and this is the phase, and this argument is playing a very important role, is angle, correct? So we can mark the some of the angles, like this point, correct? This point is theta gamma is equal 90 degree. Okay, and in between these 2 points, this is 0, of course, and this is theta gamma. This is theta gamma is equal, let's say, 45. Correct. In between that, you can imagine actually, correct. And let's say this point is 135 degree. This is 180 degree. This is 270, and this is 315 degree. Like that, we can make actually 225 degree. Fine. So can we do these things? Of course we can do, because we are actually working over the reflection plane, and this is going to deal with the two things. One is the amplitude, another is the angle, correct? So this is another way to find it out the things here. Fine. Now the outermost circle we can also call as these things the unit circle. Remember when we got this unit circle? Okay, so we can say this is gamma is equal 1. Mod of gamma is equal 1. Can we say? Can we say? Yes, of course. Fine. And similarly, you can find the different gamma circles. And this is somewhat very important, because just we have seen the relation between the VSWR and the gamma, correct? So these two things are directly related actually. So once you have the gamma circles, you can predict the VSWR. So what you need to do, you need to find a proper scale here to mark over the Smith chart, that let's say if I'm saying that the mod of gamma is 0.5, correct? So you need to find it out, this thing, a scale. I'm going to tell you these things. Fine, but before that, let me clear some of other things. Okay, so after that we'll read the scale as well. So now let us do an example here. Okay, so I'm going to remove some of the things. Okay, so let us consider a problem, example, let's say that a reflection coefficient is given you like this 0.3 plus 0.4 J. Okay, this is x plus iy form. Now we can represent in a polar form as well. So gamma A will be 0.5 e to the power j 53 degree. Can we mark this point? Of course, yes, we can mark. Fine. So this 0.5 we can manage and 53 we can find it out. So you need to use your geometry box, correct, to do these things. Because in the coming quiz, okay, I'm going to ask the Smith chart. So please purchase a geometry box. You will get all the components there to mark the angle, protector, and this divider, and all the things you will be getting in a geometry box. So it will be really helpful. So now the thing is how we will mark these things, correct? So the thing is we know that this radius is what? Mod of gamma is equal 1. Means if I'm talking about the gamma is equal to 1 circle, correct? Now I have to mark the 0.5, correct? So I will be talking about the scales in our later classes. So what we need to do, there's a scale below the Smith chart, correct? And there are so many things: reflection, transmission, VSWR, so many things is there. So what we need to do, we need to find this thing's 0.5, which is a scaled value, okay? And you need to put these things in your divider, and you have to mark over here, keeping this fact that is a center point, and let's say this is 0.5. And but before that, you need to find it out the 53 degree. So like 53 degree like must be somewhere here, correct? So if you mark like this, so this point particularly is providing you that what this magnitude is definitely is 0.5, and this things will be this angle will be 53 degrees degree, correct? Even you can do another way also, that this is x value and this is r value. Oh, sorry, just a minute. So just a minute. So this is r value and this is x value. What you need to do, you need to find it out the circle of r is equal 0.5, 0.3, and x circle of 0.4. So if you please try to download the Smith chart, correct? I'll show you next class also these things, correct, in a detail. So what you can see in this Smith chart, that different r circles of different values and different x circle of different values will be there, correct? It is mentioned over the Smith chart, correct? So what you need to do, you need to find it out. Let's say a circle, let's say we identified a circle, r circle, this is a, let's say, 0.3 circle, okay? In a similar way, you need to find it out the 0.4 circle, which is the x circle, and let's say this is going like this. So the intersection will provide you the solution, okay? Otherwise you can do like this also. So in many times we will be experiencing, you will be observing in a coming classes, that we have to play with the polar these things, okay? Polar values, and we have to mark these things, because when we are doing the matching, like let's say single step matching or double step matching, so many times we have to change these things, the angle and all those things. We need to shift whole gamma this gamma circle to these things another angle. So that time we'll be using this fact. That is why I thought this should be clear to you. So in the same way, you can also do another thing, that gamma be 0.5 minus 0.2 j. So you can mark. So definitely these are the two minus are there. So it will be going down here somewhere. You will be getting at this point, correct? Because this 0.5 circle you need to identify. Fine. So 0.5, sorry, this is a 0.5 circle, I think. So this circle and minus 0.2. So let's say this is the x circle is cutting here, correct? Now what you can do, you can just connect this line. So what you can see, that this is the magnitude and some angle. So if you convert in the polar form, this will be 0.54 e to the power j 202 degree. Okay, I hope this thing is this angle, if you calculate this angle, if you calculate, this is around 202 degree. Fine. So in this way, we can mark these things on this Smith chart. Okay, the polar things, this angle and the magnitude, we can also play. Correct. Now the thing is, there's a some other points actually I would like to tell you that let's say if r is greater than 1, correct? If r is greater than 1, so the what is the SWR? SWR, you can find it out. This R means for if the R value, the resistance circle, if it is greater than the value of 1, so you can find it out SWR just making equal to R, it will provide you the value of SWR. Whereas if R is less than 1, okay, if R is less than 1, it means what actually when I say the R is less than 1, it means that RL is less than R naught, whereas here RL is greater than R naught. Fine. So in that case, SWR is equal 1 by R. Can you prove these things? Yes, definitely we can prove. There is no magic actually. I'm writing here. Everything we can prove actually. So how we can do these things? Like we know this gamma is equal RL minus R naught over RL plus R naught. Fine. And what is SWR? SWR is 1 plus mod gamma divided by 1 minus mod gamma. Fine. Now these things, this gamma could be written in terms of small r, because if we normalize with respect to r naught, so we can write r minus 1, r plus 1. Now if gamma is represented in terms of r, so why not we can do for SWR in terms of r? Definitely we can do. Correct. Otherwise what you can do, you can recall, you can use these things here and you just solve these things. Correct. So if you're putting all those things SWR, so this will be 1 plus RL minus R naught over RL plus R naught divided by 1 minus RL minus R naught, RL plus R naught. Now if you solve this, you will be getting RL over R naught. And what is this? This is what? This is R actually. So we can say SWR is R. In a similar way, you can prove for this also. Correct? So these things are really very important because sometimes, okay, directly we can predict the SWR values. Right? So graphically we can mark over the Smith chart and we can find it out these things, the SWR, standing wave ratio. Correct. So we'll be talking about the constant gamma circle